given by a sequence of Hilbert spaces. And we have constructed this sequence. And then we have the creation map, which this is an interacting flow space on the real vector space V. The creation map is a linear map from elements of V to linear adjointable operator on the Hilbert space P. And P is this. In our case, we call it P phi 0. Okay? If I replace P phi 0 by an arbitrary pre-Hilbert space H, Pn by an arbitrary pre-Hilbert space Hn, and A daga by a creation operator which increases by 1 the gradation, you recognize what we gave as definition of interacting flow space. You see? So, from the orthogonal polynomial, we have in particular an interacting flow space. But we have more, because interacting flow space has only A and A daga, because the postulate of interacting flow is that the adjoint of A must exist. Okay? So, the orthogonal polynomial give us more, because they give A0. So the A0 is the additional information given by orthogonal polynomial. In multi-dimension, the A0 is also a map, but it's better to go into a linear map from V to any vector space. Once we have fixed the base, E is uniquely determined by the images of the elements of the basis, that is the AJ, because it is a linear basis, and it uniquely defines the linear map. Okay? So, this map has a very, you see, in an arbitrary interacting flow space, what we have is in fact a linear map from the complexified over V, and the map is complex linear. In the orthogonal polynomial, we know that the map must be also reality preserving. This is another additional information. It must be reality preserving. So, this A0 comes in orthogonal polynomial and doesn't come in interacting flow. When we are in dimension 1, if we have A plus and A minus, I can always form a new, in dimension 1, for every A0, which is a Hermitian element of the adjointable operator of my Hilbert space, I can always find a new random variable, which is by definition this one. And this new random why is a new random variable? Because I know all the moments, and we are classifying random variable only by moments. So when I give you the moments, since this is a self-adjoint operator by construction, the moments of the vacuum moments, this is the phi will be the vacuum expectation value. The state phi is in vacuum expectation. Okay? So these moments Mn, by definition, phi Yn, since Y is self-adjoint, generates an abelian algebra. And so the sequence Mn satisfies the necessary and sufficient condition to be the moments of a random variable, real valued random variable. And therefore, we have a real valued random variable. We can call it epsilon tilde, which is real valued random variable. By the hamburger moment problem, we know that the Mn satisfies the condition that Mn plus n, the kernel, is positive definite, and therefore it determines uniquely in the sense of moments. Remember, not in the sense of probabilities here, because the moments do not always determine the probability.
In the sense of what? Not in the sense of probability, but in the sense of
moment. You see, it depends on what you see. In probability, people very rarely speak of equivalency, but when we study algebraic probability theory, it's very important, the notion of equivalence. So, the implicit notion of equivalence in probability theory is that two random variables are equivalent if they have the same probability distribution. But you can also make another equivalence relation. You can say two random variables are equivalent if and only if they have the same moments. This is moment equivalent. It's a weaker relation than standard probabilistic equivalence, but is also used in probability. Okay? It is mathematically it's perfectly legal equivalence relation. Okay? So we say that we determine the random variable polynomially or up to moments, up to moment equivalence. And this is the big difference, because if you go to multi-dimension and you define, that is, if B is greater than 1, and you define the obvious analog of this equal by definition and you define like this, then what you can say about this? The problem is that if we want that this yj will correspond to a vector valued random variable, with coefficients in R, so yj and yk will be multiplication by a real function, so they commute. But if a, j are arbitrary, how do I know if they commute? Then these are necessarily sufficient. This is the truth. They commute if and only if there is. And then we know that this, when we translate in kernel language, become these two. And when we translate in inductive language, they become these two. You see?
This will determine the state uniquely.
State uniquely. State is always unique. Probability measure is not unique. Uniquely with the moment. Each solution of this two compatibility equation, the unknowns, you see, look at the inductive form. Let me write also this in inductive form, so it will be complete. So the second will be, I have to restrict a plus j on n, a plus j restricted on n. This gives me a0 on n plus 1. a0 k restricted on n plus 1. And there is a minus here, and there is a plus k restricted n, again a0 j restricted on n plus 1. See? And this must be equal. This must be equal to what? To this restricted to n and you see now you have a dagger j again to n because a0 is gradation preserved. This comes with minus, and again here a0 j restricted to n, a dagger k restricted to n again. Now, by the argument, we have a dagger jn because it's purely algebraic. Once we have the restriction on, what do we need? Jn, a0 j restricted to n, and a minus restricted to n. So, induction. And we want to define now a0 in n plus 1. This is, you can consider as an equation in the unknown matrix a0j, unknown matrices a0j restricted to n plus 1 when j goes from 1 to d. This is a linear equation because all other matrices are known. So the correct statement is for each solution the theorem will be, the induction procedure will be, suppose that I have defined all a plus, a minus, and a0 for k less or equal than n. Then I solve this equation and I pick up an arbitrary solution from this. Okay? Then it should be better. You see, this is an induction from n minus 1 to n, and this is from n to n plus 1. So there's nothing wrong, but it's not completely congruous notation. You have to replace n by n minus 1 here. So instead of determining n plus 1, we determine n by induction. Okay? And this will be what?
Determine you get the first n plus 1 from n. The first c.
Okay. Essentially, you see, because here the induction step we need a jn. How can we do? Suppose that we have all the structure up to n minus 1. We want the new a0 jn. And so we take any solution of this equation where n is replaced by n minus 1. And so I get a0 jn for every j. Huh? So this is the constraint. When I have a0 jn, I can replace in this equation. Fortunately, this is not an equation because this is uniquely, once a0 jn is fixed, everything is fixed. Because this comes from the induction. Huh? So everything is fixed. So once I have the new a0, the imaginary part is uniquely fixed. So what I can say, remember, what is the log? What is the log? The logic is a dagger is given by what I wrote there. I realize x a dagger j restricted to n is given by a xj restricted to n minus a0 j restricted to n minus a minus j restricted to n. So in order to define the new a dagger on, in order, that is, once I know this 2, I know the j dagger n that will go from Pn that I know to Pn plus 1 that I didn't know. So Pn plus 1 in the inductive construction will be defined as the linear span of the A dagger Jn applied to Pn when J belongs. Now I know. And since I know the explicit form of A dagger, I know that by the induction assumption, Pn is a monic space. Remember, monic space means that it has a monic basis. So, if I have a monic basis, here I am multiplying by some polynomial that these are polynomials, okay? So, these are polynomials of degree less or equal than n. Here I increase the degree by 1. But when j varies among d in all possible way, I get all monomials of n plus 1 order. So also Pn plus 1 will be a monic space. Okay? So this is the first step. This just I define as a vector space. Now I want to define in the inductive procedure the scalar product in n plus 1.
Yeah, you can have a tea break.
Huh?
You can have a tea break and then continue.
Okay.